This is our presentation on nuclear energy by Cooper Lavoie.
Michael Schafferon.
Leo Zong.
Nuclear energy has been a controversial source of energy ever since its discovery in the mid-20th century. Nuclear power works by splitting the atoms of radioactive fuel, such as uranium, to create steam to turn a turbine. It seems complicated, but it really isn't. However, it isn't completely safe. The byproduct of nuclear power, nuclear waste, is a highly radioactive substance that is detrimental to human and all of life. It's also very hard to get rid of. Our only means of getting rid of it is storing it somewhere. As a result, the approval of nuclear energy is in jeopardy. Often put directly and associated with nuclear disasters, uranium continues to get a bad rap. We would have to find a viable replacement for it, one that doesn't make much waste and is much safer. And if we can do that, nuclear power's popularity and reputation can be saved. Next slide, please. Our problem is that nuclear waste is not the exception, but it's the rule. That means that it's always going to be a byproduct of all nuclear production. It's also toxic to human health and the environment around it, and moreover, it takes thousands of years to get to be safe. Next slide.
One solution to the issue at hand is to invest in thorium-powered nuclear reactors. There are many different proposed designs for these reactors, and they are all different from conventional nuclear reactors that are currently being used today. A scientist by the name of A.N. Shmelev, who has written over 80 publications in affiliation with the National Research Nuclear University, discusses a potential thorium reactor. Quote, "The proposed development of the International Closed Nuclear Fuel Cycle concept by including thorium-blanket hybrid thermonuclear reactors in it will allow the entire potential of both uranium and thorium to be used." End quote. If this reactor is developed, it will allow us to not only begin using thorium in the nuclear fuel cycle, but also continue using uranium if necessary. However, uranium still produces lots of nuclear waste, and thorium doesn't have that problem. According to Pal Bagla, who has written several books and is an expert in reporting on the Indian Atomic Energy Program, quote, "Compared with uranium, the standard reactor fuel, thorium is more abundant and harder to divert to weapons production, and it yields less radioactive waste. Thorium-based fuels yield much less high-level radioactive waste than uranium or plutonium." End quote. So thorium reactors would solve the issue of nuclear waste by reducing the production of it drastically. Now, what's the catch with all of these benefits then? Well, the major caveat to this is that thorium reactors are still heavy in development. A researcher by the name of Srikumar Banerjee, who was awarded the Shanti Swar Bhatnagar Prize for Science and Technology in Engineering Science, stated that, quote, "Feasibility of the scheme of converting thorium-232 to uranium-233 and subsequently fissioning uranium-233 to produce nuclear energy is demonstrated in several countries. However, no major power plant has been built with uranium-233 as the main fuel." End quote. Scientists are still trying to develop thorium power plants that can be used for commercial energy, and more time is needed for this research. And there's also the issue that switching to thorium-fueled reactors wouldn't eliminate all of the waste that's already been produced by old and current nuclear reactors.
Another proposed solution is to store high-level nuclear waste in 500 to 1,000 meter deep geological deposits called repositories. These underground facilities would then be stored in geologic areas with rocks such as granite masses. According to the World Nuclear Association, this often termed a multi-layered concept with waste packaging, the engineering repository, and the geology providing all barriers. The waste packaging is usually made from a strong kind of metal such as iron or steel, and such repositories provide insulation of nucleotides by using rock, salt, and clay. Some downsides with the system are improper sealing, which can cause nucleotides to leak out very fast and very easily. And some damages caused by earthquakes can also cause really detrimental effects, as these repositories crack, it'll weaken the foundation that they're based on. However, there is a way to counteract it. This way to counteract it is to use stronger and thicker rock to counteract the fractures that have been made. Another solution, probably the easier one, is to relocate it from these fractured areas into other non-fractured geologic deposits. These are a lot easier to access than one might think, so it's a feasible solution.
Alright, so the best solution that we identified was deep geological storage. So the best solution is that because while thorium reactors would produce less nuclear waste than current nuclear reactors, it still produces some amount and does not permanently reduce the amount of nuclear waste that is being put out, and it does not eliminate past nuclear waste. However, geological deposits allow for nuclear waste to be safely contained and sealed in strong metals such as iron or steel. Even though seismic activity can break the sealing chamber, it can be safely relocated and stronger man-made barriers can be provided with more protection. So this is the best solution basically because although there's still nuclear waste being created, it's more safely contained than as it is currently. And those